let me start recording and let's jump to our lecture. So as always, reminders. We have final exam. I changed this a little bit, so I misspoke, but final exam is going to be Wednesday, the 11th of May. You should put this on your calendar. It's going to be 2 hours long. It's going to be online on Blackboard, but it's only going to be available during that chunk of time. Right? I feel I was trying to be a little bit more flexible with folks, but then I realized it makes things more complicated to like have it open for the whole day. But yeah, so just plan to have that time slot available. You should have been planning to have it available anyway, because that's the normal slot we would have had our test here. And then in addition to that, I will be on the Zoom meeting like for our normal lecture during that time. So if you are running issues into, Blackboard's not working, or you have questions about a particular question or whatever, feel free to hop on Zoom. I think that's allowed, right? Yeah, cool. Okay, yeah, I don't know. Anyway, that's the update on that. And here are so please fill out the Meta EIR survey. Yeah, I just thought about that. I'll have to look more into this to see, because I want you guys to be able to ask questions, but I guess you can always post on Piazza or something. I will try to make sure. Oh, you can't. Oh, it's completely locked down. So how do you ask questions? You just don't? So what if like there's like a mistake on the test and okay. So that's some drawback. All right, I'll try to think to see like the trade-offs between. So are the only two options to completely lock you guys down and then to make it just open to everything? Okay, that's not a very happy middle ground. All right, I'll look into it and I'll let you guys know as I decide, but just, I'll try to be reasonable. The other thing is, the Meta EIR survey, you guys are doing really well on this one, actually. I just checked in with Chief, 41 people already filled it out. So great. I'm happy about that. I like it, but I do feel obligated to remind you guys, you should probably also fill out the Blackboard one. Like, I don't really care as much. I don't really see the results of that, but like this gap here is, like if you're filling this one out, just fill this one out too. Okay. Yes, and that says a Sunday night and then 41 out of 62. If we get this one to 90%, which I think you guys will, because you're very close to it, +1 bonus point to everybody. Homework 10 is due on Friday. It was released last Friday. It's only written. There's no coding on this one. And this is the last required homework for the course. So originally I had planned to have 12 homework assignments. We ended up merging a few of them, like spreading them out in like a different order than I had originally thought we were going to do them. There is one assignment left that I want to give you guys, but it is not going to be required. But it is going to be covering, because this one covered a little bit of max flow, min cut, MST. I do want to teach you guys some stuff that we're going to learn today, on Wednesday, and on Friday that are more advanced, more like graduate level topics you might cover. And I want to give you, I want to give you the opportunity to like at least look at what an assignment might look like and maybe practice it on your own. But it's not going to be, graded at all. It's not going to be required. You can just, yeah. Cool. But the policy is still the same. I still dropped the lowest two. So like nothing changes for you guys. Cool. Also, if you guys remember for the homework, you can submit like retakes if you guys are doing that. So like there should be a little bit more time for you to study, but also if you have missed some homework assignments, this is your opportunity to make them up and resubmit them. Just email me to try to coordinate that. Well, I need to submit final grades, I think, on May 16th. I think it's when they want me to boop, and then click submit. It would be nice if you could get them in by the time we take the final, because at least that gives me a few days to really try to grade stuff. Yeah, that would just be nice for me. Obviously, if you if you're the only one and you get it to me like on the 15th, right before, like if I have time to grade it, I will try to grade it. But you know, if everybody does that, then I won't have time to grade all of them. So I can't guarantee it. So probably like try to aim for the final. Like by the time you take the final, try to get all your stuff in. And yeah, cool. Yeah, so basically it's like as long as I can still update your grade, I'm happy to try to do it. Just do the thing. What have we learned? All right, so let's get started. Yeah, so today we're going to cover something called stable matchings. So let's recap a little bit what we learned over the last few lectures. We learned that max flows and minimum cuts aren't just for railway routing, even though that's how the algorithms were invented in a very, very cool story. They can also be immediately applied to several other routing problems, but they're also useful for assignment problems. And can we do better than state-of-the-art max flow? Here's a question you guys should always ask yourself. So this paper actually came out March 2022. So it's like, what is that, like 3 months? 2 months? A month and a half old. Yeah, 1 month old. Where they are trying to improve the max flow algorithm that we covered in class. So the max flow algorithm we covered in class is basically the best known algorithm for how to solve maximum flow problems. Okay. And these guys improved it to O of M to the 1 plus linear time. You don't need to know this. It's not on the exam or anything, but just FYI, like this is still, again, all of the stuff we cover is, most of it is still an active area of like, can anybody think of anything better? So they're still working on this. So like we mentioned last week, we talked about ST cuts and ST flows. This is something you should know. The min cut max flow theorem says that minimizing the cost of the cut is the same as maximizing the value of the flow, and the values are the same. Okay, so that's like, you should know that. I may ask you this on a final exam theoretically. We also know that the Ford-Fulkerson algorithm is an algorithm that finds maximum flows. You should be familiar with how the algorithm works. You don't necessarily need to know all the little details, but you should know that you first find an augmenting path in the residual graph, and then you try to increase the flow as much as possible. And you basically repeat this until you can no longer increase the flow because you can no longer find any paths. The other thing to keep in mind is that max flow, the finding the maximum flow is an important primitive for solving other problems. And we're actually we're gonna move off of that, but I do want to remind you guys that we solved it, for example, to figure out how many tubs of ice cream to give to different students, how to like figure out a matching for like who gets what swag, right? So these are problems that you might not think are maximum flow problems, but they are. All right, so today we're gonna do matching when both sides have preferences. So again, this is a problem we covered last time where we're trying to match students to different swag items, and we set it up as a maximum flow problem. Okay. The main thing that we knew is we had that the students had a particular set of preferences. So that's what these arrows indicated. It's this student would like to have either of these two t-shirts. He's happy with both, but yeah. Today, what we're going to do is we're going to say, what if the swag items also want certain students, right? So again, it doesn't make sense for this problem statement, but we're going to make a new problem where it makes sense. So if both sides of the bipartite graph have preferences themselves. Okay. This is actually a real problem. Again, like this is what I was asking you guys about medical students that if you knew, but when you go into, like when you're training to be a doctor, you need to get into a residency program. And actually the algorithm, the way it works is each of the residents list a preference for the hospitals they would like to be a resident in. And every hospital looks at all of the students and also lists the preferences for which doctors they would like to take in. Okay.
Didn't that algorithm win a Nobel Peace Prize?
I feel like it is there. There's something there. I'm not sure, but I would not be surprised if there's something like, I don't know about the Nobel Peace Prize part, but it's definitely a famous algorithm. Yeah. So, see, Mike has a bit of static. Oh, sorry about that. I'll see if it keeps going, just let me know and I'll try to switch out the mics or something. Cool. My God, it's hot today. you guys not have like this school? Okay. Anyway. Okay, so to summarize, right? So the difference on what we're doing today is that we now are both sides of the bipartite graph are going to have preferences. This is not going to be solved with maximum flow. We're going to talk about a different algorithm called deferred acceptance. It's also named after the authors of the algorithm, but yeah. So for example, again, this is the residency problem. Most people have to do a residency, which is similar to an internship. You know, in contrast, most of you end up doing your internships during undergrad. See, being a doctor kind of sucks. You have to like go to undergrad, then you go to medical school, then you do a residency, and then you make a lot of money. All right. So like I mentioned, the problem statement is each doctor is going to have a preference over different hospitals. So this is the hospitals they want, and they're going to be ranked. So there's like, you know, this is the one I want the most. This is the second, this is the third. And each hospital is also going to have preference over the doctors. So they're going to say, this doctor is the one I want. And the question that we're trying to solve today is like, how should you match the doctors with hospitals? So which hospital goes to which doctor? Because once they're matched, we're going to assume that each hospital can only take one doctor. That's not in the real world, what happens is instead of having hospitals, you have positions. So a hospital might have 10 positions, and then you can just consider each of the positions independently. So here's a graph, or here's an example. So this is, I just looked up some hospitals in the area. I don't know if these are famous for you guys, but I don't know. There's Cone Health apparently here, and then there's the Brenner Children's Forest Baptist Health Hospital. Anybody heard of those? Yes, some? Okay. So this is what the graph might look like, where each doctor has a preference, right? And what we're going to do is we're going to say that the higher the number on the edge, the more they want to attend that specific hospital, right? So, for example, this doctor really wants to go to Brenner's Children's Hospital. This doctor also really wants to go to Brenner's Children's Hospital. So both of them, it is their top preference, right? It is the one that they're willing to maybe pay the most money to attend, or like they're the one they want the most. Now, both of them cannot go because each hospital, this doctor prefers this hospital. So that's the black dash line. This hospital has the biggest preference for this doctor. So the brown lines are the hospital preferences. The black lines are the doctor preferences. Okay, so they go both ways. Yeah, so that's the example we have here. What would be the matching for this specific example that maximizes the value? So everyone is as happy as possible. And by that I mean like when you take a particular edge, you know, add up all the edges that you take. So you're gonna have 3 edges because there's 3 things here. So you're gonna need to select 3 edges that have the maximum weight, where no one thing is assigned to multiple doctors and no one doctor is assigned to multiple hospitals. Anybody have any suggestions for which edges? Who do you? So this doctor, for example, which hospital would you assign them to? Brenner's. Okay.
Like, are you saying like which one they prefer, or like, so like, are you asking us like how to weight?
For this specific problem, there's going to be 3 assignments that you're going to do because there's 3 doctors and 3 hospitals, right? For this specific problem, I just want you guys to think, what are the 3 assignments that maximize the sum of the weights of each assignment, basically? Because, you know, this doctor really preferred, you know, like a 9 means, hey, I really want to go to this hospital. But obviously, this hospital also really would rather have this doctor, right? So you might say, hey, maybe this, you know, but once you take this edge, this 9, this doctor can no longer match that hospital. He has to match with this other hospital for 2, right? So there's many different possibilities.
And not so like the doctor
Yes, the doctor in the middle, he only has one preference, but you can match them to some other, like as long as there's an edge between them, you can match them. It just would be you would get the weight of the edge for the hospital in a way. But that is a good point, which is like we're basically assuming that the preferences of the hospital and the doctors are equal, so then they're comparable to each other. Yeah.
I think that first doctor would go to Brenner's.
Okay.
I think the second doctor will go
To the end. Yeah. Cone House. Yes, that is correct. How'd you figure that out? But what was the process? How did you try to figure it out? Yes, that is the highest sum. It is the highest sum. Okay. Yeah. So your algorithm. So you're saying your algorithm was like, I looked at all the numbers and looked at the biggest ones, and then maybe like, went in order from the biggest and kind of tried to pick the edges that fit, right? Okay. That's a good algorithm. That is not an algorithm we're going to cover. There are some edge cases, but I do think there is a version of this problem that can be solved by that algorithm. If you you always want to try to be more precise. Anybody else try anything different for when they were trying to figure out who matches with who? No? You just looked at it and you're like, I knew the answer. Yeah, just like came to you. That happens to me too. I look at my homework assignments and I'm just like, yeah, it's like easy, like, okay. Yeah. So the algorithm you were describing, I say, is actually known. I think it is a version of the Hungarian algorithm. We're not going to cover it. It's more advanced than what we're going to do. But if you're interested, you can Wikipedia that. And I think what you talked about is similar to that. So we're actually going to solve a simpler problem, which is, oh, okay, sorry. So let's talk about this first. So in the real world, there's some more challenges to this problem. One question you should ask yourself is, where does the input come from? As in, like, you guys are taught very often to solve an algorithmic problem. I give you, I'll be like, I give you a tree that has these properties. I give you an array with these numbers, right? But in the real world, what might be a challenge with this particular problem that your algorithm doesn't necessarily think, like, we haven't thought about yet? Because you have like real people. Let's say this is the real problem, right? You're trying to figure, there's real people that want to go to certain hospitals. There's real hospitals that want certain people. And you're coming to them and you're, hey, I am going to develop an algorithm for you to figure out the best way to match you all up, right? What would be some concerns? You'd be like, hey, yeah, Vincent? Yeah, so one thing might be, hey, like the most optimal solution doesn't mean everybody's happy, right? It does not mean that everybody gets their top choice, right? Like, for example, even for this example, I think, or you can imagine, there could be examples where just two doctors want to go to the same hospital and they just can't, right? So somebody's going to be not the happiest. Let's keep, any other issues? No? Okay. Well, here's a few. So the first thing in the real world you might worry about is the doctors could lie to you, or the hospitals could lie to you. Because if they know how your algorithm works, they could be like, well, maybe I only tell you my top choice, because then you have to match me to my top choice, right? I don't tell you, hey, I kind of want this hospital, he's my second, right? Or I lie to you, I tell you my second choice is actually all of the other choices I hate. I could not live there, right? They're the worst possible. So that's one thing you could worry about. Right. So this doctor lies and he's like, no, these two hospitals, like, don't ever match me with Cone Health. Don't ever match me with that one. I can't live there. It's impossible. Right. So that's something you might worry about in the real world that your algorithm might have to consider. Something else you might worry about is that, wow, that's some bad coloring there. Some doctors and hospitals might prefer to match outside your algorithm. Right. So maybe instead of using your process and you're like, hey, I'm going to match everybody, they decide, I think I found a better, like this hospital wants me and I want it more than your algorithm. Like your algorithm's not matching us, but we want each other more. So we're just gonna go match on our own. And now your algorithm doesn't have all the data, and you're losing people, right? So we're actually gonna focus on the second one a little bit. We're actually going to talk about something called stable matchings. Okay. So a stable matching, it turns out this is a stable matching for our original problem. A stable matching is given a matching, right? So a matching is just a pairing from everybody from one side to the other side. That's a matching where you're telling me this doctor goes to this hospital, and for every doctor you have a hospital, and for every hospital you have a doctor. Okay. What's an assumption that we're making here, by the way? That may not hold in the real world. When I say like we're gonna find, yeah, go ahead on Zoom. Sorry, who was that? Do you want to repeat yourself? I couldn't quite hear you.
Are you talking to me?
Yeah.
Oh, there's not an equal amount of hospitals and doctors.
Okay, so Leander says that one possible issue is there's not an equal amount of hospitals and doctors. Okay, why is that not a problem? It is a problem, but like, how would you solve it? What's an easy way to solve that problem? Yeah. This says blocking pair, and this says, yeah, and they're the same word, blocking, BLO, like I said, preventing something from happening. Yeah. That is a problem you might consider, which is, what if I have more doctors than hospitals, more hospitals than doctors? The algorithm we're going to talk about today in class assumes that the number of hospitals and doctors is the same, but you can very easily add like dummy hospitals or dummy doctors, and then just set their preferences to be the lowest possible, so that if you end up matching with the dummy hospital, it just means like, oh, you don't get matched, right? Because there's not enough hospitals, so there's not enough doctors, right? But anyway, so first of all, a matching. So given a matching is just, for every doctor there's a hospital that they go to, for every hospital there's a doctor. A stable matching, or I guess the first thing we're going to define is something called a blocking pair. So a blocking pair is two items from each side where they prefer each other, they prefer each other more than their assignment. So they got assigned. So the doctor gets assigned to a hospital. There's another hospital he likes better. Okay. And that hospital got assigned to a different doctor, but they like this doctor better. Okay. So yeah, I guess like, for example, this would be a blocking pair. If it happened to be the like N, this doctor really prefers to go to Brenner's hospital, right? And in addition, Brenner's hospital prefers this doctor. Because if that's true, then they don't want to use your algorithm. They'd rather drop out and then just match together, right? Because your algorithm is matching this guy to this cone health and this guy to this guy, right? So that is considered a blocking pair. If you have one of those, that's blocking. If you don't have any blocking pairs, you have a stable matching, right? So this definition of stable matching, M is stable if there are no blocking pairs. These two are equivalent definitions. So basically a stable matching is for every single pair, every unmatched pair. Dr. I prefers the thing they match to over all other hospitals that they didn't match to. And then hospital J prefers the doctor they matched to over Dr. I. So for every pair that didn't match, they prefer their current match to the thing they didn't match to. We're going to go through a few more examples, so it might make more sense. Which of these problems does that solve? So if we had an algorithm that gave you stable matchings, which of these problems we identified does it solve? If I can guarantee you my matching will be stable. Problem 2, right? If I can guarantee you my matching will be stable, you will have no incentive to go outside of my algorithm. Because you're guaranteed that even if you might not be happy, that's still a problem. You might not get your top choice, but your top choice didn't want you anyway. So, it's not like you could go outside and be like, hey, let's get together. It's like they didn't want you anyway. Okay. Yeah, and you guys thought about that already. So Now, here's another question. Does it solve the first problem? So far what we've talked about, it does not. What we've talked about so far does not solve the first problem. So you might still be worried that the doctors will lie and tell you the wrong preferences to try to manipulate your algorithm in order to get what they want, but not what is optimal for everyone, right? So if you guys are interested in thinking about algorithms that do that, where you have to consider how like the inputs are changing, should look into game theory in the computer science stuff. So, all right. Yeah, so they never prefer, so this is stable matching. They never prefer matching outside. Now we're going to cover how do we actually find stable matching, stable matches. So again, the input to the algorithm is going to be the doctors and hospitals, and everyone's going to submit preferences 1 through n. Okay. We're going to output a stable matching. So we are going to discuss an algorithm called the deferred acceptance algorithm that guarantees for every, this is actually hard to prove, so we're not going to prove it, but for every bipartite graph where you have preferences, a stable matching exists. So first of all, like that's not obvious, I'll say that. So if you don't get why a stable matching exists, that's fine. It is not obvious, but we're not going to prove it in class. And we are going to, but the algorithm we define is a way to prove it in the way that it always gives you a stable matching. Cool. So for example, this is Alice and Brenner. These are the preferences. This is another example. So who wants to propose some algorithm for this, for finding a stable matching? How would you? So I say I already proposed one, which is very different. Any no other suggestions? I'll tell you, it's kind of greedy. So it's not a hard algorithm. It's just like it's a little greedy. Yeah. Find the largest sum combinations of the. Not quite. I don't think that will work, but that is a good idea. Think about, any other ways to try to do it? Like in the real world, if you were trying to match your friends with what they like, what method might you try to use? Yeah. See the doctor's preference, check it against doctor's preference. Yes, it's actually simpler than that, but yeah. Yeah, you guys are trying to be a little bit too clever. I would say, how would you try to simulate this happening in the real world? So it's not even like we're not trying to find something like clever, like, hey, if I add these numbers together, or like I do this thing, like it'll give me the answer. It's more of like, there's a bunch of people that want to go to certain hospitals. There's a bunch of hospitals that want those people. How do you think they might sort themselves out? Yeah, Serena? Yeah, all of these are good ideas. None of them were the naive attempt I had on the slide. Oh yeah, what? So you have the rankings. You do have the rankings. You do need to rank them. Yes. What would you do after that? So let's say a doctor comes in and he gives you his preferences of hospitals. What would you want to do? Given his preferences, what would you do? If he tells you this is my favorite hospital, this is my next, what? Yeah. And like all the hospitals are open, but this is the greedy, right? It's like one person comes in at a time. They walk in, they say like, these are my favorite hospitals. Yeah.
You just give him this one thing,
yeah.
And then the next one, they're favorite.
Yeah. So that is very close to the actual algorithm. Nobody thought of this, which is fine. It's fine. This one doesn't work, but this is the actual algorithm. So as a doctor comes in, you try to match him to his favorite hospital. Okay. If his top choice is available, you go ahead, you say like, hey, you're probably going to end up there. Let me just put you there. Okay. Whenever you have a conflict where a new doctor comes in and he's like, this is my favorite hospital, right? But there's already a doctor you put in that hospital. Then you ask the hospital, which of these two do you prefer? And you give him the one he prefers, and you unmatch the other doctor. he goes back, like he goes to the back of the line again and is like, you're going to come back again in the future. I'm going to try to put you back into your favorite hospital, but I can't, you know, you will never put him back into the first hospital because that hospital has now, that hospital has matched with a doctor that prefers the hospital and the hospital prefers the doctor more. Okay. And that is the algorithm, and that works. And it always gives you a stable match. Any questions on the description? Cool. So, okay, yeah, I kind of gave you guys the whole algorithm, I guess, but there is, yeah. So the first greedy attempt is you might just try to match all of the doctors to the hospital they prefer the most. And then if there's a tie, you might say like, oh, I'll match you to like your second most preferred hospital. Okay, that doesn't work. You need to be able to, you need to free the doctors to come back again. So here's an example where that first version doesn't work. So here's the doctors, these are the hospitals they prefer. So Dr. A and B both want to go to hospital X. They have the same preference, let's say. Dr. C wants to go to hospital Y, but there's only 2 hospitals. Okay. X prefers Dr. A and Y prefers Dr. B. Okay, so if we follow the algorithm, Dr. 1 walks in, we match him to X, right? Because that's the hospital he prefers. B walks in. Who do we match B? So B, oh my God, my slides are very, okay, step up. So AB wants X, C wants Y. So we match A to X. I think B we skipped because he wants X, but X is not available. Okay, so we match C to Y. But the problem with that algorithm where it's like just match them to the ones that are available and skip them otherwise is that this pair now, so BY is blocking because B has a preference for Y and Y also has a preference for B. So they would rather match each other outside of the algorithm because you didn't assign them to each other. Okay. So the point of this example is to notice that just skipping the doctor is a bad idea. So what you want to do is you want to ask the hospital, do you prefer this doctor? And not skip him permanently, but add him back to your list of free doctors. So you come back to him in the future. And then in that way, if he does not end up with his first preference, he will end up with his second preference. If for some reason there's another doctor who wants that second preference as well, and that hospital does not want the first doctor, he gets freed again, but eventually comes back to his third preference, for example. So he keeps getting knocked down until he finds his favorite hospital that also wants him above everybody else. Okay. This is called the deferred acceptance algorithm. Okay. This was discovered in 1962 by Gail Shapley, I think. So there's a paper about it. They received the Nobel Prize in economics for this algorithm in 2012. So I don't know if, yeah, that might be what you were referring to, yeah. So there you go. So if you guys discover some new algorithms, you might get a Nobel Prize in the future. Right. So the main issue with the original version is if you try to match each doctor to the top choice, if you discover there's a blocking pair, you switch the matching, right? So you just go ahead and ask the hospitals, well, who would you rather have? I'll switch you to that guy, and then we'll put the doctor back in the line. Okay. So for this example, at the very first step, A and B both want X, so we assign A to X because he came first. Okay. C wants Y, so we match AX and CY. But now we discover that BY is a blocking pair, so we switch B and C. We switch them. Okay. So our matching ends up being A to X and B to Y for this example. And then C just ends up by themselves. Nobody wanted C for this example. We're going to walk through more examples. So it'll be a little bit clearer.
This is like actually how it would happen.
Yes, this is so actually again, look, we're not being super. This is similar to the Maxwell algorithm. So I will say this about algorithms in general. The simple algorithms are usually the ones that are really clever. Once you get to more difficult algorithms, a lot of the algorithms we have are just, you kind of try it. You like just run through an example of what this might look like in the real world, and that is your algorithm. For like Max Flow, for example, it was the same thing. We're just like, find a path and try to push as much as you can through it. And then you have to spend a little bit of time trying to argue like, hey, this is correct. But the algorithm is not, I don't know, it's not super clever, right? There's nothing like crazy about it. It's just like try to push as much flow. This algorithm's the same. If a doctor comes in and he has a preference, just like give him to the first hospital he wants and then keep going. So this is the pseudocode. All right. So while there's an unmatched doctor, so while you have a free doctor, try to match I to his next favorite hospital. If the hospital doesn't have a doctor yet, then they're both happy. So you keep that matching and you keep going to the next doctor, right? If the hospital already has a doctor, then ask the hospital, out of the doctor you have now that the doctor I'm trying to give you, which do you prefer? Make that matching and make the other, whichever doctor ended up unmatched or does not have a hospital, he goes back to the line. Okay. So here's an example. So you guys walk me through this. So how would the algorithm work? So these are the doctors, Alice, Bob, and Charlie. These are the three hospitals, X, Y, Z. These are the preferences in order. So that means Alice wants to go to X, then Y, then Z. Okay. Similarly for the preferences for the hospitals. So who wants to run me through the algorithm? One person run me through the whole thing. No, I'm kidding. You can share. Yeah. I saw. No? Do you wanna run us? It's okay. Just for yeah, and we're gonna go, the doctors are gonna walk in this order from like Alice to Bob to Charlie. So Alice walks in first. Who do you assign them to? Yeah. So Alice gets assigned to X. Okay. What happens next? So that's actually okay. So we only check the hospital preference if there's a conflict. So the very first thing is Alice wants X, X is empty. So we'll assign them. We'll start with that. It might change, right? Because the algorithm keeps going. But yeah, so what happens next? So now Bob walks in. Who do we assign him to? Yep. All right, then Charlie walks in. So the algorithm says, look at Charlie. Where does he want to go? He wants to go to Y. However, Y already has a matching. So now look at the two doctors that are being considered. Look at Bob and Charlie. Okay. Which does the hospital prefer? So yeah, Alice, but Alice is not being considered right now. We're actually only, so out of Bob and Charlie, the hospital prefers Bob. So this matching stays. So even though we looked at Charlie, he does not get assigned to his top choice hospital. So this matching stays, and we know he will never get assigned to hospital Y. Okay. So then we keep going. Charlie is still free. So what's his top choice now? Now it's Z. So Charlie gets assigned. So we try to assign him to Y. There's a conflict. So he stays, and then we assign him to Z, right? And that's it. That's a stable match, right? Here's another example. Who wants to walk me through this one? Yeah, David. We're going to talk about that. Yes, because there really shouldn't, in a way, why do I ask the doctors first? Why don't I ask the hospitals first, who they want, right? We're going to talk about it. It will give you different matchings. The matching will always be stable. So people will be like, they will not be able to get a better thing outside of the algorithm. But there is a big difference in the results. And we're going to talk about them. And I'll give you a hint. So the difference, or the main difference, you can think about why. When you do the doctors first, it is guaranteed that the doctor will get it is doctor optimal. They will get the best possible hospital they could have gotten in any situation. Okay. That makes sense, where like the preferences are respected, right? And there's no blocking pairs, right? However, it is also guaranteed that the hospitals will get their worst possible. So where it's still not blocking, so nobody wants to match outside, but they will, like, if they could have had like A and C and they're both not blocking, the hospital is guaranteed to get C. The doctor is guaranteed to get their top one if they're the same. Okay. So it is called so when you run it this way from the doctors, it's called doctor optimal. When you run it the other way, you can also run it the other way. It is called hospital optimal. And an interesting corollary to that, which brings us back to the question, are you incentivized to lie? So if it's doctor optimal, the doctors will not lie. There's no incentive for them because they are going to get their best possible choice anyway. So they should tell the truth. They don't want to game the system. However, the hospitals are very incentivized to game the system and lie if they know you're running the algorithm this way. Okay. But anyway, who wants to finish running me through this example? You guys should be prepared to do it in a, yeah, sure, give it a shot. Yes, Alice goes to X. Bob goes to Y. Mm-hmm. Yeah, so Charlie wants Y. Yeah. Yeah, so then they end up, we end up keeping Charlie with Y because the hospital wants him more. And then technically he gets freed up, so he loses his matching. And now he wants X, right? Right, so now, I should have added an extra slide. Now Alice is empty because she doesn't have a matching. And now we go back to Alice. Who does Alice want? Alice wants Y. So now Alice tries to go to Y. Right. Yes, so now the hospital prefers Alice. So now Charlie is the one that has no hospital. So now we go to Charlie, he wants Z, so he ends up at Z. And that is, so there can be a lot of movement, right? But the main thing that you should notice from this example is there can be a lot of switching, right? But it's limited. You can only switch so many times before you'll be finished. Why is that? Yeah, Jonathan, you wanna? So this is now asking, like, let's talk about the running time of the algorithm. How long? Yeah, and do you wanna know? All right, I say you wanna give it a shot? Yeah, so if we have N doctors, let's say N, and we have N hospitals, what you'll notice is that every time we switch, we ruled out a hospital preference from the doctor. So it always makes progress. We always move at least one. So the number of times, so these pointers, for example, in the worst case, they can only swap N times because each doctor, or for each doctor, they can swap N times, and then there's N doctors. So how many times can they swap in the worst case? N squared, yeah, N squared, okay. So this process of like, who is my favorite hospital? Let me try to assign myself to that. And if I get a conflict, let me switch, right? That will happen N squared times. How long do you guys think it takes to be like, you know, who is Bob's, like if you were actually implementing this, you have to look up who is Bob's current favorite hospital. Then you have to go to the hospital and look up who do you know, if there's a conflict, who do you prefer between these two doctors? What do you guys think would be the running time of doing that? I haven't told you how to represent it or anything, but this is like open question for you. Yeah. Yeah, so yeah. So you probably want to store all this information in an array, and then just to look it up would be constant time. So you repeat the process N squared times worse, and each time is O of 1. So this algorithm actually has a running time of O of n squared. Now, another interesting tidbit about this algorithm is how big is the input? So the way I defined n, I said I had n doctors, but the input that goes to the algorithm is not of size n, actually.
So like the number.
Because you,
Like subtract by the amount or like the amount of doctors, because there's only so many hospitals, right? And
Yeah.
not everyone gets matched, so the input.
so two things. So we are going to assume there are n hospitals and n doctors. So there are going to be just exactly enough to match. The input is going to be every hospital needs to tell me who their list of preference, and every doctor needs to tell me their list of preference. So how big is the input? Yeah, David. Yeah, so like let's say n is the number of doctors and also the number of hospitals. Can you define it in terms of n? N times b. What is b? Number of yeah. So the number of vertices is going to be n as well, right? Or well, 2n, but yeah, O of n. What were you gonna say? I say it's n squared. Did you? Yeah. So the input is n squared. The running time of the algorithm is n squared. So in a way, even though the running time is n squared, it is like linear in the size of the input. So there is no algorithm that you could use that would be better than this, actually, because the input alone is n squared. So you have to look at everybody's preferences, right? Cool. This is the deferred acceptance algorithm. Here's the pseudocode for it. And yes, you would probably use some sort of array data structure to both keep track of the preferences and keep track of who you are currently considering. So again, you have a big while loop that's going to run n squared times. So while you have some free doctors, so what data structure would you want to use for free doctors? Is it like a list of doctors? Yeah. Yeah, stack works fine, sure, because you can pop and push stuff off it. Yeah. List works fine too, because you can add and remove. A lot of data structures work fine. What you really want though is you want the ability to add a doctor and remove a doctor in constant time, because that's what you're going to be repeating, right? This is just saying that for hospital H, we're going to assign him to his preferred one for the current. And then if H is free, we do this. If the hospital already has a doctor assigned, we compare to see which doctor they prefer. Yeah. Again, any data structure that gives you add and remove in constant time would be great for this, because and that's another way to try to think of like how to implement algorithms when you look at the pseudocode, would be to consider what are the things I'm doing a lot of, and then is there a data structure that lets me do that in constant time, or if there isn't, can I find a data structure letting me do it in log n time, because you want to minimize the amount of time that takes. Yeah. Cool. And we already talked about the running time. Sense squared, you guys figured it out. Great. So let's skip that. We are going to, I'm not going to go into too much detail on the proof because I don't think we have too much time. You should always ask yourself these two questions about an algorithm. Does it work and how long does it take? The answer is yes, it does work. Okay. We're going to skip most of this. But this is the outline for how you might want to try to prove it. There's 3 different claims. Yeah, question? Yeah, if the number of doctors in hospitals is not the same, what you can do is, let me see if I can, so for here, if I had more hospitals that had their own set of preferences as well, I can add a dummy doctor who's either has no preference or all his preferences are like strictly worse than the other people. So you can force it to match and then if you end up matching that doctor, that means, oh, that hospital doesn't get anyone, right? So yeah, so essentially it's like you have like you had special nodes that mean if you match to this, you didn't actually match to anyone, yeah. And then you run the algorithm as normal because it assumes there's an equal number for each. We're at 12:50, so that's going to be it for today. That is it for the stuff. Nah. We still have 2 more lectures. That's not it. You're still responsible. That's it for the stuff we're going to cover with graphs. So next lecture, starting next lecture, we are going to cover NP, P versus NP. So it's a really cool theoretical thing in computer science. Get excited. And we're going to cover some more advanced topics like randomized algorithms. If you guys have done linear algebra, there's going to be some really cool thing. A really cool algorithm that uses linear algebra. Who has taken linear algebra? Okay, a good number. Okay, so maybe yeah. You guys can help explain it to the other folks. There's not going to be a homework assignment on it, so well, there's going to be an optional homework assignment. But yeah. All right. That's it for today, guys. It's 12:50. Thank you for coming, everybody on Zoom, and thanks for you coming in person. I appreciate it. Yeah.